So in this video, we'll be exploring the REDI robot simulator and mainly line sensor. So how does the line sensor work? If we get some kind of line here, when the sensor is to the one side, it goes from 100. When the sensor is aligned, it returns 0. And when the robot goes to the other side, it returns negative value. When the robot is aligned, we need to make the robot go forward, so we need the addition trick. So what we are going to do is we just put here some kind of value. Let me put here some 20 or something, then do some addition, and from the line sensor we just add it up and put it in the left motor. If we do the same, we need to invert so that the robot will rotate over itself and create a negative feedback loop so that it will follow the track. So from here we go to the inverter, from the inverter we go to one side of the addition, and from the constant we also go to the other side of the addition. From the result we put the result on the right motor. Now hopefully if we start the simulation, the robot will go forward and center itself, because whenever it goes to the one side there is correcting force, so that the robot will keep going on the track, will correct the position of the track. This will even be true if we do some kind of errors on purpose, which makes the relative position of the sensor and the track to be aligned to adjust itself, and it doesn't matter if it is the robot that is sleeping or the track that is curves feedback that actually tells the robot to keep following the track. As you can see, the robot dances quite a bit on top of the line, and this is because the reading of the line sensors on the simulation are very harsh, and it is quite normal to see 100, and when we have 100, the 100 goes to the motor and the minus 100 goes to the other. If we want to make the tracking smoother, we need to multiply the values that are actually coming out of the line sensor. So I'll just disconnect this one, and I will connect from the license sensor to the product, and then from the product to the two inputs that I had previously connected. One of them is inverted, of course. And if we put the multiplier here like 1/2, return the robot to the position, and we start the simulation, we can see that the tracking is a little bit smoother. If we get here even a smaller value, we can see that the robot does not dance as much. So this is a control effort, and we have a couple of parameters that we can play around. So if we make the constant to go forward faster, we most likely lose track to take. So if I put here something like 90 or something, we will not be able to keep track of the line following. Let us repeat that. So here there is initially some line following because this curve is smoother, and when the curve is a little bit harsh, it just loses the tracking. In order to accompany a track that is harder to keep track of, what we need is either to lower this constant going forward or reduce the multiplier, or sorry, enlarge the multiplier. So if we put here 0.75 and we replace the position, we will most likely be able to follow these curves at the expense of the robot just dancing a little bit more and becoming more nervous. We can even say that this multiplier is some kind of proportional gain, and this value k is some kind of linear translational velocity that the robot is going. So this kind of implementation is actually a proportional controller that calculates some kind of omega, so the angular velocity, based on the position error of the track beneath the robot. And thus, this is the REDI robot simulator following a track with a proportional controller.